When dealing with small heaters, typically with a full load amperage of 3 amps or 5 amps, in commercial buildings, the standard practice often involves using a 20 amps breaker for each dedicated circuit with a minimum wire size of #12 AWG. This approach generally aligns with the typical electrical design considerations for commercial spaces. However, situations exist where deviating from this norm and opting for a 15 amps breaker becomes necessary. To understand when a 15 amps breaker is appropriate, it's essential to consider the overcurrent protection requirements outlined in the National Electrical Code, specifically those related to motor circuit overcurrent protection, or MOP. NEC Article 430.52 C2 addresses overcurrent protection for motors not larger than 1000 volts. This section dictates that the ampacity of the branch circuit conductor supplying a motor must be at least 125% of the motor's nameplate full load current rating. Applying this to a 5 amps full load amperage heater, we calculate the required branch circuit conductor ampacity as 125% times 5 amps, which equals 6.25 amps. A #12 AWG wire, rated for 20 amps, easily satisfies this requirement. However, the crucial point lies in the selection of the breaker size. Although the wire can handle 20 amps, using a 20 amps breaker might not provide adequate overcurrent protection for the heater itself. The smallest standard breaker size is 15 amps, which is larger than the calculated 6.25 amps. Selecting a 20 amps breaker, in this case, would result in oversizing the branch circuit protection, potentially leaving the heater vulnerable to damage from sustained overcurrent conditions. Therefore, adhering to the NEC requirements for motor circuit overcurrent protection necessitates the use of a 15 amps breaker in this specific scenario. In summary, while a 20 amps breaker is generally acceptable for small heaters in commercial buildings, a 15 amps breaker is the more appropriate choice when considering the heater's full load amperage, the wire size, and the NEC overcurrent protection guidelines, particularly Article 430.52 C2. This ensures both compliance with the electrical code and the safety and protection of the connected equipment. To further elaborate on the considerations for selecting the appropriate breaker size for heaters in commercial buildings, let's delve deeper into the relevant factors and the rationale behind the NEC requirements. Firstly, it's essential to understand the purpose of overcurrent protection. Overcurrent devices, such as circuit breakers and fuses, are designed to protect electrical circuits and equipment from excessive current flow. This excessive current can result from various causes, including short circuits, ground faults, and overloads. Without adequate overcurrent protection, these conditions can lead to overheating, insulation damage, fires, and equipment failure. The NEC provides guidelines for selecting overcurrent protection devices to ensure the safety and reliability of electrical systems. These guidelines take into account several factors, including the ampacity of the conductors, the type of load being served, and the potential for overcurrent conditions. In the case of heaters, the NEC requirements for motor circuit overcurrent protection, MOC, come into play, particularly when the heater is considered a motor load. While heaters may not always be classified as motors in the traditional sense, they often incorporate motor-driven components, such as fans or blowers, which are used to circulate air and distribute heat. Because of this, the NEC often treats heaters with integral motor components as motor loads for the purpose of overcurrent protection. NEC Article 430 covers the requirements for motor circuits, including overcurrent protection. As previously mentioned, Article 430.52 C2 specifies that the ampacity of the branch circuit conductors supplying a motor must be at least 125% of the motor's nameplate full load current rating. This requirement ensures that the conductors are adequately sized to carry the motor's normal operating current, as well as any potential overload current that may occur during starting or operation. However, the selection of the overcurrent protection device is also critical. The NEC limits the maximum size of the overcurrent protection device to prevent nuisance tripping and to ensure that the device will trip quickly enough to protect the motor and the circuit conductors in the event of an overcurrent condition. For motors with a full load current rating of 5 amps, the NEC typically allows the use of an inverse timed circuit breaker sized at no more than 250% of the motor's full load current rating. However, this maximum size may be reduced if the motor is marked with a specific overcurrent protection rating or if the motor is part of a hermetic refrigerant motor compressor. In the case of a 5 amps full load amperage heater, 250% of 5 amps is 12.5 amps. Since standard breaker sizes are typically 15 amps, 20 amps, 25 amps, and so on, selecting the next larger standard size, 15 amps, would generally comply with the NEC requirements. Using a 20 amps breaker, in this case, would exceed the maximum allowable overcurrent protection rating and could compromise the safety and protection of the heater and the circuit conductors. It's important to note that the NEC also allows for the use of fuses as overcurrent protection devices for motor circuits. Fuses have different characteristics than circuit breakers, and the NEC provides separate guidelines for selecting fuse sizes for motor circuits. In general, fuses are allowed to be sized larger than circuit breakers for motor circuits, due to their ability to withstand high inrush currents during motor starting. However, even with fuses, the NEC limits the maximum size of the fuse to ensure adequate overcurrent protection. In addition to the NEC requirements, it's also important to consider the heater manufacturer's recommendations when selecting overcurrent protection devices. The manufacturer may specify a particular type and size of overcurrent device to ensure optimal performance and protection of the heater. These recommendations should be followed whenever possible. Furthermore, it's crucial to ensure that the overcurrent protection device is properly installed and maintained. Circuit breakers should be periodically tested to verify that they are functioning correctly, and fuses should be inspected to ensure that they are intact and of the correct size. Any damaged or malfunctioning overcurrent devices should be replaced immediately. In summary, selecting the appropriate breaker size for heaters in commercial buildings requires careful consideration of the NEC requirements for motor circuit overcurrent protection, the heater manufacturer's recommendations, and the characteristics of the overcurrent protection device itself. While a 20 amps breaker may be suitable in some cases, a 15 amps breaker is often the more appropriate choice to ensure compliance with the NEC and to provide adequate overcurrent protection for the heater and the circuit conductors. Remember to always consult with a qualified electrician or electrical engineer to ensure that the electrical system design meets all applicable codes and standards and provides a safe and reliable source of power for the building's occupants. Now, let's consider some additional factors that might influence the choice between a 15 amps and 20 amps breaker for small heaters in a commercial building. Firstly, the presence of other loads on the same circuit could be a determining factor. If the heater is the only load in the circuit, then the calculations based on NEC Article 430.52 C2 would be the primary consideration. However, if other loads are connected to the same circuit, the total load on the circuit must be taken into account when selecting the breaker size. The NEC requires that the total load on a branch circuit not exceed 80% of the rating of the overcurrent protection device. This is to prevent overloading the circuit and causing the breaker to trip. For example, if a 5 amps heater is connected to a circuit that also serves lighting and receptacle loads, the total load on the circuit must be calculated to ensure that it does not exceed 80% of the breaker rating. If the total load exceeds 80% of 15 amps, then a 20 amps breaker might be necessary, even though it exceeds the maximum allowable overcurrent protection rating for the heater itself. In this case, it may be necessary to install a separate circuit for the heater to ensure that it is adequately protected and that the circuit is not overloaded. Secondly, the type of heater being used can also influence the choice of breaker size. Some heaters, such as resistance heaters, have a relatively constant current draw, while others, such as heat pumps, have a variable current draw that depends on the operating conditions. For heaters with a variable current draw, it's important to consider the maximum current draw under all operating conditions when selecting the breaker size. The NEC requires that the overcurrent protection device be sized to protect the circuit conductors and the equipment being served. This means that the breaker must be able to carry the maximum current draw of the heater without tripping, while also providing protection against overcurrent conditions. For heaters with a variable current draw, it may be necessary to use a larger breaker size to accommodate the maximum current draw, even though the heater's nameplate full load current rating is relatively low. Thirdly, the ambient temperature in the area where the heater is installed can also affect the choice of breaker size. The NEC requires that conductors be deaerated for ambient temperatures above 30 degrees Celsius or 86 degrees Fahrenheit. This means that the ampacity of the conductors must be reduced to account for the higher ambient temperature. If the heater is installed in an area with a high ambient temperature, it may be necessary to use a larger wire size to compensate for the deareting of the conductors. This, in turn, may affect the choice of breaker size. For example, if a #12 AWG wire is used in an area with a high ambient temperature, its ampacity may be reduced to less than 20 amps. In this case, it may be necessary to use a 15 amps breaker to protect the conductors and the heater. Fourthly, the length of the circuit run can also influence the choice of breaker size. The NEC requires that conductors be sized to minimize voltage drop. Voltage drop is the decrease in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends that the voltage drop on branch circuits not exceed 3%. If the heater is located a long distance from the panel board, the voltage drop on the circuit may be excessive. In this case, it may be necessary to use a larger wire size to reduce the voltage drop. This, in turn, may affect the choice of breaker size. For example, if a long circuit run requires the use of a #10 AWG wire, which has a higher ampacity than a #12 AWG wire, a 20 amps breaker may be appropriate, even though the heater's nameplate full load current rating is relatively low. In addition to these factors, it's also important to consider any local codes or regulations that may apply. Some jurisdictions may have more stringent requirements than the NEC, and it's important to comply with all applicable codes and regulations. Ultimately, the choice between a 15 amps and 20 amps breaker for small heaters in a commercial building depends on a variety of factors. It's important to carefully consider all of these factors to ensure that the electrical system is safe, reliable, and code compliant. Consulting with a qualified electrician or electrical engineer is always recommended to ensure that the correct breaker size is selected for the specific application. Furthermore, to provide a more comprehensive understanding of the factors influencing breaker selection for heaters, it is beneficial to consider the specific types of heaters commonly encountered in commercial buildings. Firstly, electric resistance heaters are a prevalent type, utilizing a resistive element to generate heat. These heaters often feature a straightforward design and are typically employed for space heating or localized heating applications. The current draw of electric resistance heaters remains relatively consistent, simplifying breaker size calculations based on the heater's nameplate amperage. Secondly, heat pumps are frequently utilized for both heating and cooling purposes. These systems transfer heat between indoor and outdoor environments, offering energy efficiency. Heat pumps incorporate compressors and fans, which introduce variable current draw depending on the heating or cooling demand. When selecting a breaker for heat pumps, it is crucial to consider the maximum current draw during peak operation as specified by the manufacturer. Thirdly, infrared heaters emit radiant heat, directly warming objects and individuals within their vicinity. These heaters are often employed in outdoor or semi-outdoor settings, such as patios or warehouses. Infrared heaters can exhibit varying current draw based on their design and wattage rating. The breaker size should be selected to accommodate the heater's maximum current draw, ensuring adequate protection. Fourthly, forced air heaters utilize a fan to circulate air over a heating element, distributing warm air throughout a space. These heaters are commonly used for space heating or supplemental heating applications. Forced air heaters typically incorporate a motor-driven fan, which contributes to the overall current draw. When selecting a breaker for forced air heaters, it is essential to consider the combined current draw of the heating element and the fan motor. In addition to the heater type, the installation environment can also influence breaker selection. For instance, heaters installed in damp or wet locations may require ground fault circuit interrupter (GFCI) protection to prevent electrical shock hazards. GFCI breakers are designed to detect ground faults and quickly interrupt the circuit, reducing the risk of injury. The NEC mandates GFCI protection for certain types of equipment installed in specific locations such as bathrooms, kitchens, and outdoor areas. When GFCI protection is required, a GFCI breaker must be used, and the breaker size should be selected based on the heater's current draw and the requirements of the GFCI device. Furthermore, the presence of other electrical equipment in the vicinity of the heater can also impact breaker selection. If the heater is installed near sensitive electronic equipment, such as computers or medical devices, it may be necessary to use a surge suppressor to protect the equipment from voltage spikes or transients. Surge suppressors can be integrated into the breaker panel or installed as standalone devices. When surge protection is required, the breaker size should be selected to accommodate the surge suppressor's current draw, as well as the heater's current draw. Moreover, it is essential to consider the coordination of overcurrent protection devices throughout the electrical system. Overcurrent protection coordination involves selecting and coordinating the ratings of overcurrent devices, such as circuit breakers and fuses, to ensure that the device closest to the fault will trip first, minimizing the extent of the outage and preventing damage to upstream equipment. Proper overcurrent protection coordination requires careful analysis of the electrical system and the characteristics of the overcurrent devices. In some cases, it may be necessary to use different types of overcurrent devices, such as reverse time circuit breakers and current limiting fuses, to achieve the desired coordination. Additionally, it is crucial to maintain accurate and up-to-date electrical drawings and documentation for the building. The electrical drawing should show the location of all electrical equipment, including heaters, and the size and type of conductors and overcurrent protection devices. This documentation is essential for troubleshooting electrical problems and for making future modifications to the electrical system. Finally, it is important to remember that electrical codes and standards are constantly evolving. The NEC is updated every 3 years, and it is essential to stay current with the latest requirements. Consulting with a qualified electrician or electrical engineer is the best way to ensure that the electrical system meets all applicable codes and standards and provides a safe and reliable source of power for the building's occupants. In conclusion, selecting the appropriate breaker size for heaters in commercial buildings is a multifaceted process that requires careful consideration of various factors, including the heater type, the installation environment, the presence of other electrical equipment, and the coordination of overcurrent protection devices. While a 20 amps breaker may be suitable in some cases, a 15 amps breaker is often the more appropriate choice to ensure compliance with the NEC and to provide adequate overcurrent protection for the heater and circuit conductors.